Hi, here we have another question from Iranian Mathematical Olympiad round number 1, year 1997. The question is related to algebra, the topic polynomial. We have, suppose f and g are two polynomials with real coefficients and of degree 2 or higher. We have this equation, fx2 is equal fx minus 1 over 2 times gx plus 1 over 2. It asks us to prove that gx is positive for all value of x. First round of Iranian Mathematical Olympiad is usually consists of multiple choice questions. You get 30 questions for 3 hours. Each question approximately 6 minutes. If you answer correct, you get plus 3 points. If you answer wrong, you get minus 1 point. So you have to answer them very accurately. Now, in the actual question, obviously, we had multiple choices. So these were the options. A, for every n equal or larger than 2, there exists such polynomial such that f is a polynomial of degree n. B, no such polynomial exists. C, the polynomial fx has a root in the interval between 0 to 1.5. D, the polynomial gx has a root in the interval between 0 and 1 over 2. And E, the polynomial gx is positive for all value of x. I evaluate the question to be moderate degree of difficulty. So maybe I spend 10 minutes, try to solve the exercise, and then come back and see the solution. All right, now let us look at the solution. This is the equation that is given to us. Fx2 is equal to this. In these cases, usually we can write the general format of a polynomial. So obviously fx can be written as, for example, an x power n plus an minus 1 x power n minus 1 till a0. And for gx, we can write it bm x power m plus bm minus 1 x power m minus 1 till b0. All right, so in this case, maybe we have to look at the limit of polynomial when x goes to infinity, plus infinity or minus infinity, and see if we can find additional information. Because when x goes to plus infinity, the whole polynomial will approach to the first term. So in this case, for example, from the left side of the equation, fx2 will be approaching to an multiplied x power 2n, because all the other terms are very small compared to the first term. Therefore, the limit of fx2 x goes to infinity will be an x power 2n. For the right side, the limit of fx will be an x power n, and the limit of gx will be bm x power m. And because these two multiplication has to be equal to fx2, therefore an multiply bm times x power m plus n should be an times x power 2n. And that means because an exists in both sides, so bm has to be 1, and also m has to be equal to n. So we obtain some information, but this information does not help us to answer the question. We have to do something different. All right, so now in this case, what I did is that I assumed that fx has a root, and I call that root x0. So fx0 is equal to 0. Now I'm going to create another x such that this side of equation becomes 0. So obviously I can consider x is equal to x0 plus 1 over 2. If I plug this one into here, then we will have x0, which means this side will become 0. Okay, so in this case, f x0 plus 1 over 2 power 2 will be equal to f x0 times g x0 plus 1. This plus half becomes x0 plus 1. And because f x0 is equal to 0, we can conclude that f x0 plus 1 over 2 power 2 is equal to 0. Okay, so we assumed one root and we obtained another root. So that is some new information. But the important part here is that let's evaluate this new root that we obtained, x0 plus 1 over 2 power 2. It becomes x0 power 2 plus 2 times first one times second one plus x0 plus the second one power 2, 1 over 4. And if you compare this one now with the initial x0, of course, x0 with x0 disappears, and x0 power 2 plus 1 over 4 is always larger than 0. Therefore, we conclude that this new root is always larger than the initial root that we assume, x0. So if we have one root, x0, we can always find another root that is larger than x0. And now we have this new root. Again, we can find another root that is larger than this. And this process can repeat infinitely. Therefore, we conclude that fx has to have infinite number of roots. And obviously, this is impossible. Therefore, we cannot have any root for fx. Same way, we can assume that gx has a root, x0, Okay, gx0 is equal to 0. In that case, we consider a new root, x0 minus 1 over 2, because we want to create this side equal to 0. In that case, f x0 minus half power 2 becomes f of x0 minus 1 times gx0. This is 0. Therefore, f of x0 minus half power 2 becomes 0. So if gx has a root, we also find another root for fx. And if fx has a root, we already mentioned that this is contradiction, because if fx has a root, it means that it must have infinite number of roots, and that is not possible. Therefore, it means that gx can also not have any real roots. Okay. So we wrote gx as bm x power m plus this one till b 0, and we said that bm has to be 1 from the previous slides. And now we know that gx cannot have any roots. So obviously, if x goes to infinity, the limit of this polynomial becomes the first term, and bm is positive, so this whole term becomes positive. And since the polynomial doesn't have any real root, it means that the polynomial has to be always positive. And with this, basically, we can already show that the correct answer is option E. The polynomial gx is always positive. Because obviously, we showed that fx cannot have any root, gx can also not have any root, so these two options are obviously wrong. The first option says for every n equal or larger than 2, there exists such a polynomial that f is a polynomial of degree n. This cannot be true, because if the polynomial is an odd degree, then the polynomial has always one real root. And therefore, it will be contradiction, because we showed that fx cannot have any real root. Therefore, this statement is also wrong. But now what about option B? No such polynomial exists. We have to also eliminate this option. Okay, so in the previous slide, I have shown that if we have an x0, then we can find another root which is always larger than x0, and that led us to conclude that fx cannot have real root. What about imaginary root? In that case, this equation can actually have a solution. X0 power 2 plus x0 plus 1 over 4 is equal to x0. X0 with x0 disappear, and x0 can be I divided by 2 or minus I divided by 2. So in this case, we can construct fx as equal to x2 plus 1 over 4. And obviously now I can put this one here, and I can calculate fx2. I divide them, I can get gx. I have done this already, so I'm going to do it other way around. Assume that gx is also x2 plus 1 over 4. So let's evaluate fx minus half. In this case, will be this term power 2. So first one power 2, x2, minus first one time the second one time 2. That one gives us minus x plus 1 over 4. And we have another 1 over 4. It gives us 1 over 2. And gx plus 1 over 2, same way, it becomes x2 plus x plus half. And if we multiply these two together, so this one plus this minus x, this one plus this plus x. So it will be first one power 2 minus the second one power 2, which becomes basically x4 plus x2 plus 1 over 4 minus x2 becomes x4 plus 1 over 4. And that is equal to fx2. So we actually found a solution that fx2 is equal to fx minus half times gx plus half. So therefore, this option is also wrong. So the correct answer will be option E. Let's see what we have learned through this exercise. First thing is that evaluate the term with the highest degree in the polynomial. Take the limit of polynomial when x goes to plus infinity or minus infinity, and look for the additional information that you can obtain by this process. Determine and investigate the roots of the polynomial, whether they are real or complex. Evaluate the coefficients of the polynomial. Try to see if you can extract extra information. Determine if the polynomial is always positive or negative. If the first coefficient is positive and the polynomial doesn't have root, it means the polynomial is always positive. If the first coefficient is negative and the polynomial doesn't have root, it means the polynomial is always negative. All right, so that's the end of the video. I hope that you learned something new. See you next time. Bye.